Right, so I'd like to talk about model predictive control in Julia and give an example of a workflow using the JuliaSim toolkit. So first of all, an overview slide that I borrowed from Frederick Carlson, who's the team lead of controls. And this is basically of the big picture of JuliaSim control toolkit. So which is much wider than this talk alone. So it has support for PID control. It has support for linear control analysis, robust and tuning, robust control, and so on. But in particular, I'm looking at this piece, which is an MPC control. And we can think of MPC control as having sort of three components. So the first is this prediction model component. So the idea is you have a model that determines the future evolution of your system, and then tries to optimize, give you a set of optimal control inputs, such that you can optimize this future trajectory. So this first component is this prediction model, and then we'll have a set of inputs we'll have a set of inputs that are sent to control inputs that are sent to the real model, to the real plant. And then from the real plant, we'll have a set of measurements from which we'll have a state estimator, an observer, usually some kind of Kalman filter. And from the state estimation, we return to the prediction model for the next time step. So with that overview, I would like to present basically an example of a workflow, and in this case, of a workflow of linear MPC, but with a nonlinear plant model, and split into these 6 steps. So the first step is we build a nonlinear dynamic system model, and this is usually based on domain knowledge. And in this case, a nice interface, as was presented earlier, is with this with the modeling toolkit to define the model symbolically. And once that is done, we could obtain a feasible trim or equilibrium point. And so trimming is much larger than obtaining an equilibrium point. And in this case, that would be using the trim functionality within JuliaSim control. And this usually involves formulating and solving a constraint optimization problem. And in this case, using optimization.jl that Chris also talked about earlier. Once we have this equilibrium point, the third step would be to look at that first prediction model. So if we linearize about this trim point, we would have this linear prediction model, and this can be done using ModelingToolkit, the linearize function. Then to get the nonlinear observer model for state estimation, in this case, it would be an uncentered Kalman filter. There is this another open source package developed by Frederick called low-level particle filters that allows for this functionality. So I'll present each of these in turn. Then step 5 formulates, builds the whole thing together. So the 3 pieces: the linear prediction model, the nonlinear observer, the nonlinear plant model, using the MPC toolkit, and again solves the MPC optimization problem with optimization.jl. And then the 6th step is all about surrogatization. So this is a new feature, which is we try to surrogatize the MPC for fast and optimizer-free control, closed-loop control. So, and in this case, it would be with Flux, and another package within JuliaSim called MPC surrogates that I'm working on, and it could also be done in a on a GPU with CUDA. And I would like to show this acceleration of 150x. Individually, I've been involved in this trim tool and in the surrogatization tool. So I suppose the motivation for organizing things like this. One overview is the high-level overview of the model predictive control is we can deal. We can deal with linear, nonlinear dynamics and observers, allows robustified tuning and models from FMU and ModelingToolkit. It allows also, as mentioned, allows for high performance solvers and surrogatization of the controller for optimizer free operation. So in many ways, the appeal is on speed. So we see that we're able to solve linear MPC problems at over 4,000 hertz, nonlinear MPC problems at around 1,000 hertz with the tool, and then solve surrogatized MPC problems at, say, 1 megahertz. And this 1 megahertz number is something that I hit on one of the test problems in this classical Bemporad-Morari Pistikopoulos paper that introduced explicit MPC, a very highly cited paper, and in that we were able to hit this one megahertz. Cool. So introducing the case for today, which I think is an example of a dynamic system of intermediate complexity, which is of this nonlinear research civil aircraft model. So I'm sorry about that. So here, the idea is you have this aircraft and you have 9 states. So you have you could have forward translational velocity. You could have sideways velocity. You could have velocity going up and down. And then you could have rotational velocities, so about the x-axis, about the y-axis, and about the z-axis. And you could also have rotation angles. So you could have this roll or bank angle, which is sort of the angle about the x-axis, and then you would have a pitch angle, which is basically the aircraft on takeoff, for example, and then you would have the yaw angle. And then we have 5 control inputs, which would be the aileron angle. I'm sorry. Which would be the aileron angle. This is the right and the left aileron angle, the tail angle, the rudder over here, and then the left engine throttle and the right engine throttle. So we picked this as an example because it has fast nonlinear dynamics. For example, when we want to discretize, a good sampling time was in the order of 0.02 seconds. So it's not kind of some chemical engineering problems you can do 30 seconds, but here it's like 0.2 seconds was necessary. And I also think it's an intermediate complexity problem, as I'll try to show. So in the first step, we would do symbolic modeling using ModelingToolkit.jl, which is an example that provides acausal modeling and provides high performance structural simplification algorithms, and as mentioned, also provides an interface to the control or MPC toolkit. So to do this with ModelingToolkit, it's in 2 steps. The first, we define using these parameters and variables macros. We'll define a list of parameters. We'll define a list of variables and a fairly complicated list of equations in this case. And then we'll build the ODE or DAE system. So there is this lecture over here, which is a 1-hour lecture by Professor Christopher Lung, who gives the derivation of the equations that I'm going to show. It's a 9-step procedure, which I'm not going to present. I'm just going to give the results. So I'll switch to the Pluto notebook and hope it looks fairly good. Oops, that's too much. All right. Okay, that's too much. All right. I hope that's good. So, right. So with the symbolic modeling with ModelingToolkit, we begin by defining certain fixed parameters in this case, which are a number of constants. We define certain inertia matrices and so on. And then using the parameters macro, we get all these parameters. We input the parameters into the system. In this case, there are quite a few representing sort of various aerodynamic correlations. And then the next step, as I mentioned, is we define the variables, which in this case are the states and the controls. So as I mentioned, we have these 9 states over here, and we have 5 control variables: aileron, tail, rudder, and the 2 engines. Following this, there is this procedure, which is not. There is this procedure of developing this 9-step procedure of developing all the equations symbolically. So I'll skip these for the most part. So this is where kind of the domain knowledge comes in. Right. So, right, it's rendering. All right, so that's a 9-step procedure. And then this is basically the set of equations. I think we have about 133 equations list over here. So I would say it's an intermediate complexity model, and some of them are fairly. And
the logic automatically generates itself in the notebooks.
Right. Yeah. There's very nice printing going on. Right. And yeah, I would say some of the differential algebraic equations are fairly complicated. So then the next step would be, in case we want to get some intuition on the model, to basically do a simplification and a numerical simulation with the differential equations.jl toolkit. So in this case, we would, for instance, do a structural simplification given the list of inputs, a list of outputs. In this case, I assume all the states can be are sensed, which is an assumption. And then yeah, I can set that, and then I go from this large list of 133 equations, which are differential and algebraic. After the structural simplification, I get the small 9. It reduces to 9 different differential equations. Although they are quite complicated, it's still substantially simpler than earlier. And then we can simulate them, and again, we can get these plots to get some intuition of what's going on in the system. So, for instance, this is the forward speed of the aircraft, and we see if I have this initial conditions, I'm able to, with the initial conditions and initial parameter set, the speed goes up, and then everything sort of starts to stabilize. So this is the forward speed of the aircraft, the side speed is 0, and so on. All right, so then we move to the next step, which is to determine a feasible trim or equilibrium point. Great. And right, so here the idea is you pass in the system you got from ModelingToolkit, for instance, the RCAM model I just presented. You pass in a list of inputs, in this case, a list of control inputs and a list of outputs, which you would be able to sense. Yeah. Then you pass in a list of parameters and say desired state. So here in this case, I would like to give a specification, user-defined specification that I want my trim state to be steady state, straight, and level flight. So by default, trim gives you a steady state, so the derivatives are set to be 0. But you may also want to have non-zero derivatives. For instance, you might want to have a trim state that is steady acceleration, as an example, or a banking turn, for instance. So so the trim functionality is more elaborate than what I'm presenting over here. From that, so then we specify this. We can also specify a list of hard equality and hard and soft equality and inequality constraints. And then since we're formulating and solving a constrained optimization problem, we could pass in some solver parameters. So here I would like to trim about a straight and level flight. So I would like to set the airspeed to say be 85 meters per second and no side slip velocity. And I don't want my aircraft to be trimmed on this state. I would like it to be straight and level. So I set the other states as mentioned. So that's what I put here. I can specify a list of hard equality constraints, hard inequality constraints. In this case, this would be saturation limits on the controllers. So basically minimum and maximum angles of the controllers. And then a few other things. And then I would call the trim function within JuliaSim control. And that would give basically the states that I am interested in. So it will tell me that if I want to get as close to 80 to have steady state level flight at 85 meters per second, I need to basically set my controls in this, and then if I'm left here, I'll continue at steady state straight and level flight. So that sounds like a great point about which to linearize the ODE system, and in this case, the ModelingToolkit.linearize tool. Again, the documentation is written here. The ModelingToolkit.linearize tool comes in. So this gives us the linear state space system in these delta coordinates, and once again put in a set of inputs and outputs, and then put in the trim point. So as an example, so for the example, right, so we call the linearize function and get the A, B, C, and D matrices, and initially it will be a continuous time system, and these are, I don't have horizontal scroll on this, but okay, right. So we'll be able to get these A, B, C, D matrices directly out of, and these exactly correspond to the one presented in the YouTube tutorial. Following this, we could discretize the dynamics to give a discrete time LTI system. And this is, again, very familiar with the C2D system and choosing the sampling time. All right, so, okay, hope that's fine. So then the fourth step, so right now, just as a recap, we have this three pieces of MPC we want to put together. We have the linear prediction model set. So the next step is to look at the nonlinear observer model, and in this case, it would be this. We could use an extended Kalman filter. We could use an unscented Kalman filter. Unscented tends to work slightly better, slightly higher computational cost, but works better in this case. So then, so this provides a way to take in the measurement from the real system, and assuming we have Gaussian measurement and dynamics, Gaussian measurement noise and Gaussian process noise, basically gives us a good estimate of, or an optimal estimate with those assumptions of the state. So then here we'll have we'll need to put in the dynamics function, which is the internal model of the unscented Kalman filter of the plant, and a measurement function. In this case, would be a bit of Julia code, like a runtime generated function. So and also these covariance matrices of the noise. So R1, R2, and R3. I'd like to mention that over here in the documentation, there's also an unscented Kalman filter for differential algebraic systems that has been built. So right, there is a bit of bookkeeping here, and then basically we call the unscented Kalman filter, use the unscented Kalman filter function with the dynamic systems we have built, and giving in the appropriate matrices. So we would need to have a wrapper around the operating point, and the point of this is to negotiate between the real coordinates and the delta coordinates that we use in the linearization. All right, so now we have all the parts we need for the we have all the parts we need to build the MPC model. So we have the linearized prediction model, we have the observer model, and the actual dynamics, which we had built using ModelingToolkit. All right, so then we can input in these three models into using the MPC toolkit. There's this linear MPC model functionality. So we give in the prediction model, observer, and any constraints we may want to impose on MPC. We give in the operating point and initial points for the observer, and so on. A few things in documentation, and then we formulate the MPC optimization problem. So for instance, if you want to use linear quadratic MPC with this kind of state function, where Q1 are the state penalty matrices, Q2 is the controls penalty matrices, and with constraints, and then we could also give a reference to a solver in optimization.jl. And I would like to also mention that there are other examples that are more complicated. There's a webinar from Frederick on nonlinear MPC. There's a robust MPC, QMPC, generic MPC, and so on with arbitrary function cost. So this is a small slice of the tool. And so, as an example, I give this saturation constraints on the controls, set them as my only constraints for the MPC. Again, we could have much more general constraints. Formulate the MPC, formulate the linear MPC model. Basically put in these three parts, and then formulate the MPC problem with the cost function matrices and so on. So I'd like to mention I've not tuned this much, so it is just like a default value in some sense. So then we could. So I would like to present two cases if I have time. I would like to. So the first is with without any disturbances. So then we can solve this MPC problem again with within the SciML system. There is this common solve interface. So this is a method on common. This is a method of solve to MPCs that accepts MPC problem. So once we give in the initial state and the simulation time. So in this case, I would like to simulate for 300 time steps, which at 0.02 seconds turns out to be about 6 seconds. And I would like to have no disturbances, and I would like to pass in the actual model. So the actual plant model over here. So then we're able to simulate this, and then we see that, yeah, this is not that interesting. It is, we go from basically 87, which is my speed from 87 to 85, which was my trim point. And also at again, the scale of the scale of the y is within tolerance, and then we can plot out all the results of the different controls. So the more interesting one which I wanted to show is the MPC with disturbance. So here, I would like to have a sort of semi-dangerous scenario in which the fifth engine basically experiences some sort of block between time step 100 and time step 140. So not the fifth engine, the second engine, which is the fifth control input. Basically, so it the control, the additive control is like negative 40, so it's right at a lower level. So this is a disturbance that occurs in these 40 time steps. So then I can repeat the solving problem by including the disturbance, and then here, yeah, this is slightly more interesting. So here I can see this is the sort of interesting states, which are, I start from 87, which is my initial point. I have a control, nice control, right up to the trim state, which is where I have steady state level flight, which I enjoy for a few time steps. And then the disturbance kicks in right over here, and then we see that immediately it goes down, and then we're able to get the MPC control back to the steady state straight and level flight, and these are the other states as well. So the last thing I would like to discuss, which is a new feature. Yeah, right. So this is what I said. We could call the solve functionality. That's common to the ModelingToolkit and do and look at this disturbance rejection. So the last thing I'd like to discuss, which is on surrogatization of the MPC controller, so a bit on the motivation and the philosophy. So one of the most important challenge with MPC control is that you need to solve an optimization problem at each instance. So this again limits the sample rate because you need to be able to solve it before you like at a in time. So the question is, will the optimizer always converge in time? And as an example, if you have a control operating on 50 hertz sold to a million customers and so on, we could end up with like a gigantic number of QP solves, like 6.6 exponent 14, like QP solves, and not a single one may fail. So the motivation for surrogatization is that you must have a optimizer that is verified, and this is time consuming and expensive. So again, in terms of philosophy, that is the standard MPC. Sorry, that is the standard MPC. Then the other alternative is you just surrogatize everything, which is you surrogatize the observer and the controller, and that ends up being a static surrogatization. So then the philosophy here is we surrogatize the just the most challenging part, the controller part. So the idea is, so this again, if this is the controller, this is the observer, we have a sort of reference trajectory at each time step. We have the initial state estimate at that time step, and we're looking to determine the control output at that time step. And this turns out to be a fairly vanilla neural network, and that works fairly well. So, and then this eliminates all the concerns about the optimizer, like deterministic execution time, fast, and so on. And I mean, there's still several challenges with this. For instance, building trust and having good surrogate models is still very much something to be perfected on. So and this opens up a lot of things. So if you so it allows the hardware to be used for other things, because the neural network which determines which gives you the control law basically only requires simple multiplication and addition. Then you don't have to deal with determinism in the optimizer, licenses, verification, and so on. So and then we could expand the scope of MPC. So I hope that's fine. So right. So then we're working on this MPC surrogates.jl toolkit. So the idea is again quite simple. We put in a list of so eventually the hope is this will look like the GUIs Chris presented earlier, where we would have a slider for say width and so on, and then click a button to surrogatize. But then we could present say we want a width and a certain activation function, certain learning rate, and these are training parameters, and then say have a single function that says get surrogate, and then this would return a trained neural network surrogate. So I'd like to show that. Again, I chose these parameters based on some literature studies. So and also this was supposed to be a Pluto notebook, so I didn't want to run it, train it for too many. I trained it on one trajectory. Right. So I can basically put in all these features, and then call MPC surrogates.get surrogates, and then it will return this trained neural network, and also returns the training data. And in this case, this was trained with Adam, but so yeah, as I said, this was supposed to be a Pluto notebook. I had another neural network I trained further with limited memory BFGS, and that gave very low training error. And then I imported that neural network in here. So and then once we do that, we can basically call the solve functionality very similar to the solve functionality very similar to the rest of the toolkit. So in this case, we would put in both the MPC problem and the neural network, and then we would solve it. And then we see in general about 150 times acceleration, and that is with kind of a few weeks of coding, not very well optimized. And that's 150 times faster than the Julia MPC toolkit, which is already substantially faster than most other most other toolkits, and we're able to get fairly suitable control. There's quite a lot to be done, to which I'll present next, but right. So as I mentioned, the neural network in this case was trained further with LBFGS with Optim.jl, and then using this FluxOpt tools, which is an open source toolkit. We can also train it with GPU, say from JuliaSim on CUDA, and we have this additional solve method that simulates MPC with the trained surrogate. There are a number of other things left to be done, and we have a webinar on the Frederick and I would be giving a webinar on the 2nd of November, which is on trimming, linearization, and MPC design with JuliaSim, and the idea is to have integral action for MPC, which is quite important and something that was missing from the at the moment. And then the eventual goal is to have this click and surrogatize functionality of MPC. We basically have a GUI that does this well for us. Other sort of nice things like, and we also want to include work with the Julia Reach team that does reachability analysis, and see, basically to do some kind of, to see how good the surrogates are, and to perform reachability analysis with the surrogate models. If we're able to have, so the idea again in terms of enabling technology is if the surrogates work well, that also helps other pieces, like for instance, if you want to put an MPC controller in an embedded platform, then code generation becomes much simpler if we and verification and so on becomes much simpler if it's on a if it's just matrix multiplications. And then there are also other features that are available. Again, code generation partly available. Other features like nonlinear MPC with DAEs and so on. And I'd like to mention we have an open webinar coming up that discusses some of these things. Great, thank you.
About the structure, what you talked about now is the source and how much is the...
Right, so I think I can show it from this. So ModelingToolkit is open source. The JuliaSim control trim tool is within JuliaSim. Optimization.jl is open source. The ModelingToolkit linearize is open source. The low-level particle filters is open source. The MPC toolkit is within JuliaSim, and MPC surrogates is within JuliaSim. Flux is open source. FluxOpt tools is open source. CUDA is open source. Okay, right.